All right, yesterday, we ended, in part I ended yesterday with a long list of assumptions that you have to make if you're going to study speciation using a clade. So we began with the idea that if you're interested in the origin of one particular species, you have to analyze the entire clade that that species is part of, especially all of the descendants of the common ancestor of your species. So that you have to analyze, at the minimum, you have to analyze sister species and their close relatives. You also have to make a lot of assumptions about current geographic. Surprisingly, historical biogeography was a key element of Darwin's thinking. This is my most favorite passage in Origin of Species. And the reason is that what I've highlighted in yellow, this sentence only occurred in the final edition. In the first 5 editions of Origin of Species, the sentence said, the naturalist is led to inquire what this bond is. But 13 years after he published Origin of Species, Darwin was so frustrated with his colleagues that he said, if you don't know how important this is, you must be really stupid. And that was unusual for Darwin. Darwin was very careful not to antagonize people. Darwin was all about persuading people. But this is a very strong statement for Darwin. He's just basically calling out all of his colleagues and saying, if you don't understand how important geography is to evolution, you're really stupid. Of course, he was probably retired at that point. He already had tenure. He wasn't going to be in trouble by telling his colleagues they were stupid. And he didn't say that those geographic patterns of similar species were the result of natural selection. Because he said those patterns exist regardless of the conditions. There's something about the evolutionary process itself that has this geographic component. It is not that similar species always arise in the same kind of physical conditions wherever they occur on the planet. So basically what he's saying is similarities between species, no matter where they are the result of common inheritance. But geography is really important anyway. But geography is not important in a Lamarckian sense. Geography is not important in the sense of the inheritance of acquired characteristics specifically adapted to the local conditions. And then you have to go back to Darwin's, what we call Darwin's necessary mismatch, where Darwin started off by saying the nature of the organism is more important than the nature of the conditions because, and he only knew this because he was a good field biologist. He said, when we go out in the field, what we find is that the same adaptations occur in very different environments, and different adaptations show up in the same environment. So, that's like I was saying yesterday, which is better adapted to a tide pool, a crab or a polychaete? Well, that's silly. They each have adaptations that allow them to live there. But the reason a polychaete looks like a polychaete is not because it lives in a tide pool. It's because it's descended from a polychaete. And a crab looks like a crab because of its ancestry, its history of inheritance. And Darwin said, we have to take that truth, that the bonds of relationships among species are historical inherited bonds, and we have to correlate that with geographic distributions. So there's something about geographic distributions that is not convergent evolution on common environments. There's something else. And he said, that bond is simply inheritance. Common ancestry. Boom. When did we forget that? No, about 1930. Okay. One of the ways to begin to approach explanations of the large-scale diversity of the biosphere, that is, all of these different clades that all coexist on this planet, is to look at geographic distributions and ecological relationships in a historical context. And Simpson said this in 1953. He called it zoogeography because he was a zoologist. But what he said was that the geographical distributions have to do with history, and ecological relationships among species have to do with history as well. And we'll see later today, we'll see that Simpson tried to figure this out, and he pretty much got very confused for a number of reasons. Part of that had to do with the fact that neo-Darwinism was not really Darwinian. And Simpson was trying to be Darwinian, but he was also trying to be very modern at the same time. So what I'm going to do now is to talk about some basic pieces of pattern. Okay, now this is a purely formal exercise. And this word vicariance, now I'm going to introduce you to an alternative use of the word vicariance in the literature. Now yesterday, I talked about vicariant speciation. That was the original definition of the term. That's what we call passive allopatric speciation. A barrier forms, it splits an ancestral species, and you get two descendant species out of it. Okay. Vicariance today, in terms of historical biogeography in the literature, vicariance is oftentimes used as a synonym for any sister species relationships that are allopatric. And it can also be used as a synonym for any general patterns in a biogeographic analysis. So this word is used in several different ways in the literature, and you have to know which term is being used. In formal biogeography, formal historical biogeography, vicariance is used as an observation. And the observation is that you have, say, a geological history of 4 areas that looks like this. That this is the sequence of the formation of barriers separating these areas. And you find a clade of species whose sister group relationships are an exact match for that pattern. Now the assumption has been, and in fact Deborah McClellan and I used that assumption in as recently as the Nature of Diversity in 2002. Until 2005, we all believed that the only way you could get this kind of match between geological history and phylogeny was through vicariant speciation. You know, we now know that that's not true. That's not necessarily true. And we'll get into that. We'll get into that later, and then actually in 2 weeks in the advanced course there's going to be a whole lot of stuff about that. Now here's another piece of pattern, biogeographic pattern. So here are the 4 areas. And if our expectation is that everything should speciate according to these origins of these barriers, then if this is what our phylogeny looks like, our interpretation is that there should be a species in area B that has this sister group relationship in the phylogeny. It's not there. We've sampled like crazy. We know there's nothing there. Therefore, this is the result of extinction. Now, the thing that's interesting about this, that what I'll come back to a couple of times, is that that is already making an assumption of mechanism. The actual observation is there's nothing in that clade living in area B. Now, if everything is a result of vicariance, then the absence of something in area B must be the result of extinction. But that's an assumption. That's a built-in hidden assumption that we're making. All we really know is there is a mismatch between those two patterns. And the mismatch is that there is nothing in area B in that clade. The pieces of this clade, the species that are there, their relative relationships do match with that general pattern. Sympatric speciation is really easy to do. What you get is duplications. This is what happens if you have sympatric speciation in this ancestor, so that you have 2 sister species living in the same area that then experience the same history. So each of these two sister species then produces its own clade as a result of those episodes of vicariance. And this is the way you end up with two different clades living in the same areas, showing the same geographic distribution patterns. Again, here is your general geological scenario. And you go over and what you discover is that this group actually has 5 species in it, not 4. And the 5th species lives in an area that's not part of this geological scenario. So in this case, it's the opposite of the extinction explanation. In this case, you say something new and unique has been added. And there, it's allopatric with its sister species. So this is not part of the vicariance scenario. It's new. It's allopatric. Oh, that must be the result of peripheral isolate speciation. Speciation by dispersal. Here's a different kind of speciation by dispersal. This is a situation in which you have, if you take this species away, the two patterns are the same. You add this, and you have a situation in which you have a secondary speciation event that is speciation by dispersal. But instead of dispersing into a completely new area, you have dispersal into an area that's already occupied by a close relative or by a relative. That's the kind of pattern you have to see if you're ever going to investigate the possibility of speciation by reinforcement. If you don't have that kind of observation, you can't study speciation by reinforcement. And this is an example of what we call reticulated area relationships. That is, you have two species living in the same area for two different reasons. This species has lived in area A for a longer time than that species. This species lives in area A because of vicariance speciation. This species lives in area A because of speciation by dispersal. So there are a lot of historical differences and potentially ecological differences between the two species living in the same area. Now, until very, very recently, historical biogeographers did not allow that possibility in their results. And anybody who published something attempting to show those kinds of reticulations was not allowed to publish. There were specialized assumptions that you could make in methods of analysis to get rid of the inconvenient data like that. In component analysis and related kinds of studies, they're called assumptions 1 and 2. Here's a slightly different kind of pattern. If you take out that, the two are the same. This is what happens if this species originates by vicariant speciation in area A, and then later expands its distribution into another area without becoming a different species. So now you have a different kind of evolutionary scenario. This species and this species co-occur. There's a possibility for reinforcement, but even better, you have this really nice evolutionary control, because you can study this species when it's interacting with a close relative in area D, and you can study it when it's not interacting with that close relative in area A. So now you can study speciation by reinforcement with an evolutionary control. And if you use a method of analysis that doesn't allow you to find those sorts of things, then the historical biogeographic studies are not as useful as they could be. Okay. So when are these geographic patterns not enough? That's when extinctions and post-speciation dispersal change your assessment of the ancestral geographic distributions. Whenever these things happen in the history of a clade, using the protocol that I described yesterday to explain speciation will give you the wrong answer. Now, how many people think that in the history of life there have been some extinctions? I do. How many people think that in the history of life, species have moved around on the planet from time to time? Okay. Now, that's another way of saying, how many of you believe that every ecosystem on this planet is made up of representatives of different clades? If all of biodiversity was organized by vicariants, every place on this planet that had species in it, all the species in that place would be members of a clade. There is no place on this planet where we have that. So this means that these phenomena are real, important, pervasive aspects of the history of life. And if they're that important and that common, then we have to anticipate that they are going to impact any assessment of speciation modes. So how do we deal with the fact that we expect that two of those basic assumptions that I finished with yesterday are likely to be violated all the time? Well, it turns out that you can do something about compensating for that by analyzing multiple clades, not just doing one clade at a time. Analyzing multiple clades will allow you to distinguish clade-specific patterns from general patterns in the distributions of species. They will allow you to determine post-speciation dispersal. They will allow you to infer extinctions. And they will help us to assess evolutionary radiations, which is what we'll finish up with today. Okay, the first thing we have to do is, once we begin analyzing multiple clades, and I'll show you how that works, one of the other things we have to get over is this really strong assumption that historical biogeography made in the 1970s, when Cladius first started doing biogeography. We all assumed that there were things called general patterns and unique patterns in biogeography, and that we were only interested in general patterns, and general patterns could only be the result of vicariance. Okay. And you make those two assumptions, and the world is very simple. You look for the general patterns, you say it's all vicariance, and you have a celebration, publish your paper, and move on. Well, it turns out that in fact, that's not actually necessarily true. So in those examples we gave where a peripheral isolate speciation, where you have a mountain range that's isolated things, and then a little opening happens in the mountain range, and members of your species, your clade, disperse through, then the gap closes up and you have peripheral isolate speciation. Well, when a part of a mountain range opens up, or when a wet area cuts through a desert, how many people think that the only organisms that are going to disperse are members of the clade that you just happen to be interested in, and nobody else will move when that happens? That's not reasonable. So that means that there's a possibility that you can get general patterns that are the result of dispersal, not just of vicariance. And as soon as you start considering that, the whole world begins to change. And the person who came up with that observation is this incredibly bright young guy at the University of Kansas, Bruce Lieberman. If you want to know how to have the perfect academic background, you do what Bruce did. You do an undergraduate thesis with Stephen Jay Gould at Harvard. Then you go to the American Museum and you do a master's thesis with Miles Eldridge. And then you go to Yale and you do a PhD with Elizabeth Berman. Okay. Then you can say, I think I know something about paleontology and macroevolution. And then if you're also incredibly smart and a really good person, you've got Bruce Lieberman. So here's what Bruce said. He said, okay, now we all believe that there are these vicariance patterns that mimic the breakup of Gondwana, or the breakup of Pangaea. Okay? We have Pangaea, the continents start to pull apart, separate, sister species. Cichlids in Africa are related to cichlids in South America, catfish, blah, 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 and all this sort of stuff. And they're all patterns of vicariance, and this is really cool. And he said, now, I study trilobites. So I study organisms that lived on this planet before Pangea. And if you look at the movement of continents before Pangea, what you find is that it's not just all continents pulling apart. It's also continents coming together and smashing into each other. And he said, so, if you get general geographic distribution patterns when continents pull apart, shouldn't you also get general geographic patterns when continents come together? The difference is when they come together, those general patterns are patterns of dispersal. Uh-oh. Suddenly that means that you can't just look at what we call an area cladogram, a diagram of areas based on multiple clades, and assume that the general patterns on those diagrams are all the result of vicariance. You have to assume that some of them may be the result of dispersals. You know they're general, but you don't know what they are. Dispersal versus vicariance, or more accurately, dispersal or expansion versus isolation nodes. And Bruce figured out a really nice way to do this. You go to an area cladogram, looks something like this. And this is the result of combining a whole bunch of different clades together. And in 2 weeks, the first day and a half of the session in the advanced course is all going to be about the method for doing this. But we're not going to worry about that now. And what you can do is that you can begin to analyze the nodes. So for example, here you have sister species in area A and area D. So what do you think, what is your best hypothesis about the geographic distribution of the ancestor? Geographic distribution of the ancestor would have been in areas, something called area D plus area A. If you look at the next node down, okay. Oh, I'm sorry. Oh, backstroke. Okay. I forgot something here. On this diagram, the heavy lines represent the general parts of the pattern, and the narrow lines represent the unique parts. Now, what you do when you're trying to assess the ancestral geographic distribution is you don't worry about the unique parts. You're just trying to explain the general pattern. So that's why here we just take A away, and the first node, general node, is this one down here, and that's a CD node. This is general, B plus CD. This is general, A plus B and C, A, B, C, D. And then this is a unique thing. So here are the 3 nodes, general nodes. And you notice that the bottom one has 4 areas represented, the next one has 3, and the next one has 2. What kind of general phenomenon in evolution results in the progressive narrowing of geographic ranges? Well, that's progressive isolation. Okay? So these nodes would be called vicariance nodes or isolation nodes. What happens if you have a slightly more complicated situation? And again, the thin lines are unique features. They're represented by only one clade out of all the clades you're analyzing together. So you neglect them, and you're just analyzing the general nodes. Here you have a situation in which you start with 2 areas, then 1, then 4, then 3, then 2. Okay, 4, 3, 2. That's just like before. That's isolation, isolation. What about 2 to 1? That's isolation. But then we have this transition, 1 area to 4 areas. How do you go from an ancestral distribution in 1 area to an ancestral distribution in many areas? That's how fundamentally important and simple Bruce Lieberman's insight was. And the fact that vicarious biogeography had missed that for almost 30 years tells you how focused we all were on another view of the world. This is why you always have to have young people, new minds, new eyes coming into the discipline. Now here's a slightly different version. 2 areas to 1 to 4, 3, 2. You end up with, these are slightly different versions. In this particular case, the H is here, and here the H is up there. But it's a unique piece, so it doesn't affect your assessment of the general pattern. So the unique pieces don't matter here. But what you have is, this is the kind of picture you get if you have isolation, expansion, isolation, isolation. So what happens, and we'll come back to that later today, what happens is that when you begin to reanalyze published data sets that are supposed to say all vicariants, but you reanalyze them without the restrictions, without the restrictive assumptions, what you begin to find is, instead of seeing just isolation, 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 vicariance, 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 what you begin to see is expansion, isolation, expansion, isolation, expansion, isolation. Have a completely different macroevolutionary dynamic. So it turns out that not all general patterns are due to vicariance. Peripheral isolate speciation can produce general patterns when multiple clades disperse along the same dispersal route. That's how you can get general patterns in island biogeography, for example. And for 30 years, cladistic biogeographers did not analyze island biogeography because there were no general patterns there. We knew that, so we didn't even have to look. Of course, it turns out we were wrong. But so here you have what we call a general area cladogram. This actually is something that's produced from combining a bunch of data about different groups of species that live in the Caribbean. So each of those letters represents a different part of the Caribbean, except for A and F. A is Florida and B is Venezuela. But B, C, D, and E are different parts of the Caribbean. So here's what it really looks like. Those are the real geographic distribution patterns for different clades living in the same areas. And if you notice, there C shows up many times, B shows up, D shows up. You can't get that kind of thing unless there's been a lot of dispersal, a lot of movement among the islands. And it turns out that what you find is that here are all these unique things. So you have colonization from Florida, colonization from Venezuela, occurring uniquely out to the islands. So what you have is multiple independent colonization events into the Caribbean from different parts of South America, Central America, and North America. But once they all get there, they seem to have landed more or less in the same place. But then what they did after that depended on the group. So you have one central target. You then have dispersal out and an expansion onto other islands in the Caribbean, and then you start to have more differentiation. So you have colonization of an area, expansion in that new area, and then isolation in that area. So it doesn't matter whether it's mainland or islands, you see the same general dynamic for colonization-driven speciation. Okay, now, what I've tried to do here is to set the stage for you, where we say, okay, the good news is that we can analyze speciation modes, even in cases where extinction and post-speciation range dispersal, range changes, have obscured the ancestral patterns. That's the good news. The bad news is that this is going to make the whole world much more complicated than just saying, it's all vicariance, it's all continental drift, every group on this planet is 400 million years old, which is what we had with the old vicariance paradigm. So now, let's take a 10-minute break, come back, and I'm going to set this aside for the moment. Okay? Right now, this has to do with analyzing speciation patterns among multiple clades. We're going to put that aside. We're going to come back, and I'm going to talk about a different topic called evolutionary radiations. And then we're going to finish up today by putting both of those pieces together. All right. Okay. Now, I want you to just, for the moment, compartmentalize what I was talking about with biogeography. We'll put that off to one side. So one use of historical biogeography is in testing our protocols or making our protocols for studying speciation more robust. But we're going to see that historical biogeography has applications in other areas of research as well. Today and tomorrow we'll talk about that. So put that aside for the moment. Now I'm going to talk about a phenomenon that most of you may know under the heading of adaptive radiations. Okay. Now, most people believe that the concept of adaptive radiations was something that was central to Darwin's thinking. And the reason for that is because there is a mythology that has been created about the Galapagos Islands and about those little birds called finches on the Galapagos Islands. But that mythology, that story, was not created until 1950. And it actually isn't the way things happened in the Galapagos, but that's another story. Evolutionary radiations. It's true that Darwin did talk occasionally about the fact that it seemed that some groups were more successful than other groups. Okay. By the time Darwin became a biologist, there were enough practicing taxonomists that a pattern was beginning to emerge in classification that is still there today. And that is that it's typical that within a taxonomic grouping, say a family, that's made up of 10 genera, okay, even though we know these are artificial, over and over again in many, many different groups, taxonomists still end up recognizing the same thing, where if there are 10 genera in a family, 6 of those genera will have only 1 or 2 or 3 species, one or two of them will have 5 or 6 species, and then one genus will have 90% of the species in the entire clade, or the entire group. And that taxonomic pattern, if we could make the inference that that kind of repeating taxonomic pattern actually was telling us something real about biological diversification, then that's something that needs to be explained. Now, there are people who believe that that's just an artifact of the way human beings classify the world. This is important, and then there's all the rest of the stuff. Or as Dan Jansen says when he summarizes the evolutionary ecology of human beings, the selective pressures, it was the early natural history of human beings was eat, kill, ignore. Now, I of course would say eat, kill, reproduce, ignore. But Dan's much more focused on science than I am. So there are people who, you have to remember that everything I'm going to talk about now, there is a possibility that all of this is imaginary. That all of this is just an artifact of how we classify it. And it doesn't actually say anything about evolution. So that is a possibility. For the moment, I'm going to talk about this under the assumption that there is something evolutionary going on and we don't know exactly what it is. And we call these evolutionary radiations. Now, it turns out, interestingly enough, the term adaptive radiation actually originated in the one theory of evolution that had nothing to do with adaptation. Adaptive radiation actually showed up in orthogenesis. So this was a lineage would arise by spontaneous generation, and it would then evolve from simple to complex, from less specialized to more specialized, until it became over-specialized. Then it would degenerate, become a parasite, and go extinct. In fact, many of the founding fathers of orthogenesis were parasitologists. I don't know if any of you have parasitologists here know about Giardia. Some of you who've been out in the field may have had an up-close and personal experience with Giardia if you were unfortunate. But Giard, for whom Giardia was named, was one of the early founders of orthogenesis. Another one of the early founders of orthogenesis was a German named Theodor Eimer, for whom the coccidia genus Eimeria was named. So there was a very, very strong relationship between parasitology and orthogenetic views of evolution, which many parasitologists still believe today. And when we talk about coevolution tomorrow, I'll get into that a little bit more. But if orthogenesis was true, the reasoning was that one of the things we should see is a lot of parasitic species. We see a lot of parasitic species on this planet, therefore, this was taken as evidence that orthogenesis was correct. Now, Henry Osborn, who was at the American Museum of Natural History, was a really ardent orthogeneticist. He was an mammalogist, and his version of orthogenesis he called aristogenesis, because even all the way back then, Americans and Europeans had to have different names for the same thing. And scientists are always competing with each other for credit for the same idea. And one of the ways you can pretend that you are the one who came up with the idea is to make your own name for it. And we know that Osborn was unsuccessful because we talk about orthogenesis today, we don't talk about aristogenesis. But it was the same basic concept. And so here's what Osborn said constituted an adaptive radiation, was that you had this straight line, these evolutionary trends towards increasing complexity, increasing specialization, and that there were these sort of levels of evolution that each lineage would go through independently. And each one of those levels was something he called an adaptive zone. Now, he was using adaptation in the original Darwinian sense, that is, as function. These are function, we would call them functional levels today. He called them adaptive zones. And as species traveled through these adaptive zones, they underwent adaptive radiation. So that's where the term came from. It's not a Darwinian term at all. And part of the problem we have with the concept today is that there was an attempt to modify a non-Darwinian concept into sounding like Darwinism. So all the species with the same adaptive mode, you know, these kinds of teeth, these kinds of legs, these kinds of diet, they had the same adaptive mode, they were in the same adaptive zone. And everything went through a series, occupied a series of different adaptive zones, and that was their adaptive radiation. Now, George Gaylord Simpson was a student of Osborn's. And Osborn, yesterday I talked a little bit about the relationship between orthogenesis and eugenics and some of the social policies of repressive governments like the Nazis. Osborn was a real eugenicist. He was a real racist. He was like Herbert Spencer. And he really, except that Osborn thought that Americans were at the top and Spencer thought the Brits were at the top. But otherwise they had the same view. I mean, they both agreed about who was at the bottom. And Simpson didn't like that. He didn't like Osborn's politics, he didn't like Osborn's racial attitudes. And so he decided to get Osborn. He decided to destroy him scientifically. And he decided the best way to do that was to take the one original idea. Oh, Osborn also was famous for stealing people's ideas. So he decided to take the only really original idea that Osborn ever had, and he was going to take it away from him. And he was going to recast it in Darwinian terms and basically destroy Osborn that way. And they were both at the American Museum, and there was, advisor and student. So it's all the typical Gothic novel of academia and museum intrigue. So in 1944, Simpson published his classic book. Okay, he was one of those fortunate people who managed to stay at the American Museum and write an evolution book while the rest of the world was out fighting the Second World War. And in that book, he wrote this really nice piece of prose. where he talks about adaptive radiations all over the world, in every part of the world. Wonderful history of life, all the modes and factors of evolution all woven together. This is sort of the tangled bank of Darwin. And what I like about this is this phrase here, appalling intricacy. This is somebody looking at natural history, knowing something about all of the diversity of life that was known by the 1940s and going, this is too much. This is overwhelming. So, whereas in the 19th century, the canons of science said, the universe is simple. There are a few simple laws, they're very powerful, they're very general. That's what we're going to find. All throughout his book, Darwin kept referring to laws, 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 laws. The laws of inheritance. He didn't know what they were. His own theory was a little bizarre. But he knew there must be laws of inheritance, and there must be this, this, and this. But by the 1940s, Simpson's looking around and going, this is so complicated that now we have to start trying to explain all of this complexity. And there were two ways to deal with this. One was to address all that complexity, and that's what Simpson did. And then there was the alternative view that became the prevailing view, and that is, let's just cut out most of the complexity and let's study just one population of just one species. Let's study plots of one population of one species. Let's just get the geography smaller and smaller, and the time smaller and smaller, and then we can really study something. But Simpson actually wanted to try to understand all of that complexity. And he said it assumes that we cannot understand it all, but we can understand some of it. Now, here's what Simpson said. Adaptation is the result of an interaction between the organism and its environment. In order to study adaptation, we have to quantify the environment. We have to find out what it is in today's terms, what problem in the environment is being posed that the organism has to cope with. What is the problem that the organism is going to solve with a particular function or with a particular functional change, with an adaptation? And Simpson said, well, the problem with this is that the environment is very complicated. So how do we quantify something that's that complicated? Because the environment includes all of these abiotic phenomena and also includes all the other organisms on the planet. My environment includes all of you and all of them and so on. So how do we do that? And Simpson decided that what we need to do is to divide the environment into niches, into quadrats, into boxes in a diagram. And he called those zones or areas, okay, adaptive zones. He's already beginning to change the concept of adaptive zone from something that is inherent to what the organism does at its particular stage of evolution into something that is in the environment that organisms occupy. So Simpson has made the neo-Darwinian switch from the functional niche or the functional environment of an organism being something that the organism creates as a result of interacting with its surroundings into something that exists for organisms to come into and fit into. So then Simpson, because he wanted, in the 1940s, he wanted to, as a good biologist, he wanted to sound like he knew something about physics. And the really trendy physics of the day was quantum theory. So he talked about quantum evolution. Quantum evolution is the first part of an adaptive radiation. Now, there are two senses of quantum change. Okay, one sense or two senses of what we think about with when we say the word quantum. One is this idea that something can very rapidly go from one state to another state. A quantum change, we sometimes say, indicating that it was almost an instantaneous change. There's another sense of quantum And that was what came out of a set of experiments in physics that showed that one set of experiments showed unambiguously that light was a particle. And another set of experiments showed equally unambiguously that light was a wave function. And so there was a paradox, or a duality, about the nature of light. That somehow it was both a particle and a wave. And we didn't understand exactly how that could be. And a lot of the development of quantum theory has to do with trying to figure out a way to explain the nature of light, that duality, without ever coming to the point that you have to say that Einstein was correct. So even in physics, there's a lot of politics. That's why Einstein never won a Nobel Prize for relativity theory. And in fact, there has never been a Nobel Prize in physics given to anybody for any research in relativity theory. They think biologists are the only ones that do nasty things with each other. Okay, so we talked about quantum evolution. So you have these adaptive zones. Now, there are these zones out in the environment. And they're just sort of sitting there waiting for organisms to fill them up. So you, species X, are sitting in an adaptive zone. And somehow, you do a quantum leap into a new adaptive zone. You're moving to a completely new place, a new space. And then evolution takes over. So the first thing is that you have to jump out of your old life into a new life. So you have to jump from one quantum zone, one adaptive zone to another. And this, for Simpson, was accomplished by the evolution of what he called a key innovation, or a key adaptation. So, for example, if you're a hippopotamus and you evolve flippers instead of feet, you can jump from the hippopotamus adaptive zone into the whale adaptive zone. That's a shorthand way of saying that's how hippopotami became killer whales. So that's how it starts. The function of a key adaptation in evolution is that it allows a species to jump out of its adaptive zone into a new one. So what you have is, here's the adaptive zone. And the adaptive zone could be something like living on the ground. Now it turns out, and I'll get to this in a little bit, Simpson had another potential use of quantum, the word quantum, to indicate this duality. Because half the time for Simpson, an adaptive zone was a part of the environment. And half the time, the adaptive zone was something that was phylogenetic, or at least taxonomic. So he would have something like, here's the adaptive zone. The adaptive zone is living on the ground. And what you have is another adaptive zone up here called living in trees, which doesn't have any species in it. So this is the beginning of the idea that niches have an existence.